even if I am changing my data from a small number to big number, say for example 8-bit to 32-bit. Right, supposing if my 8-bit number is a positive number, after expanding to 32-bit also it should be a positive number, it should not get into the negative number, because the MSB says whether my data is positive or negative. If the MSB is 0, the number is treated positive. When the MSB is 1, the number will be treated as negative. That is actually the common name or common way of representation. So the sign extension is, without changing the positivity or negativity of the symbol, I am going to increase the size of the data. That is actually called a sign extension. Data reversing, we can transfer the bytes from the most significant byte to least significant byte, or least significant byte to most significant byte. So some sort of reversing operation is again possible, and the bit field manipulation again, which is very important. Here actually what happens, I have a data, say for example I have a 32-bit data, and this 32-bit data is used to switch on or off 32 lights. Right, it's an embedded application. So I have designed an embedded application, and using this ARM microcontroller I want to switch on or switch off 32 bulbs, lights, right, we can say. Now suppose I want to switch on the third light, right? So what I have to do, I don't know what is the present status of the light, right? Supposing if I set it, I can't make a single bit set or reset in the normal case, right? So what we have to do is, I have to update the total value into my system, so that I will get all the 32 bits, right? So what are the lights are switched on or switched off, I can read the status. Then suppose I want to switch on the third bit, I have to make the third bit as 1. Then I have to write the data, so that the data will be given to the relays at the output, and the corresponding lights will be switched on and switched off. So we need 2 or 3 instructions. First I have to read it, then I have to change the particular bit only, then I have to repost this output into operation. So this operation need to be done for normal execution. But here in a single instruction I can change the data. That is actually the main advantage here, right? I need not read it, write it. So each and every bit can be separately addressed. That is actually the address of this bit field manipulation. Normally only a group of bits will be addressed in the memory, but in the case of bit field manipulation, every bit can be addressed. That is the advantage of bit field manipulation. Fine. Then list of conditions. There are plenty of list of conditions. Say for example branching. I have to branch my control if 2 variables are equal. I have to compare, then I have to take a loop. Suppose if one value is less than some condition is satisfied, then I have to transfer the loop. So what are all the possible conditions we can check, or what are all the flags that are available? So that we are going to decide. Then there is a if-then statement. Normally if-then statement, I think you should have used it in your C program or wherever it is, right? So though the syntax will be slightly different, the if-then equivalent can be used in the ARM microprocessor. And of course there are plenty of other useful instructions, something like wait for the event or wait for interrupt and all those things, which are specific for the microcontroller. So these are all the various type of instructions which we are going to study in this particular module 2, and there are more than I think 100 instructions are available, and we'll be giving an idea about what is what. And again in your question paper actually you can see some instructions will be given, and you have to understand what is the type of instruction, and you have to give an example, and when that example is executed, what all the changes will be made. So you have to give a small explanation about it. So such questions will be asked in your exams, right? So to start with, we are going to have a data definition directives. So there are 3 data definition directives are possible: DCI, DCB and DCD. So DCI stands for define constant instruction, right? On the right hand side you can see my number, a space, DCD, a space 0x123456. So what will happen actually, this is again similar to your EQU statement which we already seen. So the number 0x12345678 will be assigned to the name called or variable called my number. This is possible. And in the second example you can see hello text, right? This is actually a text variable, and we are going to make it into DCB, right? So this hello \n will be assigned to the variable hello_txt, right? So this is actually 2 examples where we can make use of DCB and DCD, right? And on the bottom side you can see how it is used. Say for example, LDR R3 comma equal to my number. So what will happen? Whatever the my number is available, in that case actually 0x12345678. This, the address which is, the data which is available in this particular address will be loaded into R3. So that is the meaning. Again, you can go through this. Get the memory address value of my number. So this 12345678 is an address, and the data available in that particular address will be moved on to the register R3, right? Then LDR R4 comma R3, again get the value of R3 here, right? So again the data that is available in that address will be moved on to the R4, right? The next thing is LDR R0 equal to hello text. Again we are going to initialize this hello text to the register R0. So get the starting memory address where that data starts. That location will be moved on to R0. Then if you want to have a printing, then you can print in a loop. So one digit by one digit it will be printed, right? So this is how the system will be using this DCD and DCB. Again let me repeat. My number is equal to 0x12345678. This is actually the address, and the data available in that address will be moved on to R3. That is actually the meaning of this instruction. Then there is a unified assembler language, right? Actually already we have discussed there are three variations, right? There are thumb instructions, there are thumb2 instructions, then there are ARM instructions, ARM classic instructions. So there are plenty of variations are there. And this unified assembler language is useful for easily porting between thumb and ARM code, right? Of course, we have already seen the ARM Cortex M3 is using only the thumb2 type of instructions, right? Anyway, this is just for information, only for the basics, right? So the traditional thumb instruction will be something like this: add R0 comma R1. So that is the first line here, you can see. And if it is a traditional thumb instruction, the flag will be updated automatically. For after every data manipulation instruction, the flag will be automatically updated. This is actually the normal or traditional thumb instruction. But in the case of UAL syntax, you have to have a suffix yes. You can see the thing, add yes R0 R1 R0 comma R1, right? So in this case actually addition will be performed. That is R0 and R1 will be added and the result will be updated in the R0, right? But here you can see there is an suffix yes is available, and this will make the flags to update. So we have to intentionally add an yes in order to update all the flags that are available here. So you'll see the description. The yes is used to update the flags. So update application program status register, which contains of all the flags. And here there is an example, add yes R0 comma R1, right? So in this case the application program status register APSR will be updated because we have added an yes. Suppose if the yes is not there, the flag register or this particular APSR will not get updated, right? So what are the other possible conditions? Just we can see, right? Say for example EQ. Supposing for example EQ means if two values are equal. One example is there in the last line, you can see there is a BEQ. What does it mean? You have to branch if the condition is equal, right? So the equivalent is actually a condition. So if the two variables are equal, then I have to take the branch. Otherwise I have to follow in the same procedure, right? Or I have to continue further in the execution. So that is called equal, then not equal, less than, greater than, and there are plenty of instructions are of course available. So these are all conditions, and if this condition is satisfied, then only the operation will be performed. In the first case addition will be performed, in the second case the branching will be performed, right? Here we can see what is the comparison between thumb versus UAL and thumb versus thumb2. So the first line I think you can see it is add R0 comma R1. So R0 equal to R0 plus R1. So supposing if there are only two operands, the operation will be performed and the result will be stored in the first operand. Already we have discussed. So R0 and R1 will be performed and the result will be again will update the value of R0. So this is using the traditional thumb syntax. And the equivalent syntax in So the second line gives the equivalent instruction in the UAL syntax, and the third line, it's an AND instruction, AND R0 comma R1. So in this case again the R0 and R1 will be ANDed, the result will be stored in R0. Then the fourth one is AND S. So here actually we are adding in S, so that the suffix S is added in order to get the flags updated, right? So this is the comparison between thumb and UAL instructions. And what about the thumb and thumb2 instructions? So here normally what happens, thumb instructions will be of 16-bit, right? And thumb2 instructions can have both 16-bit as well as 32-bit. Both the things are possible. So we'll see one by one. The first case is add S R0 hash 1. So R0 will be added with the R0 plus 1, right? Because 1 is an immediate type of addressing, right? And based on the result, the flag registers will be updated. So that's why actually we are going to have an add S. So it is a 16-bit thumb instruction, and whenever the data is going to be only 16-bit, right? The data will not exceed 16-bit. Straight away we can go for thumb instructions, no problem. Right, supposing we are going to use a 32-bit thumb2 instruction, but we want to take only the 16-bit. So in that case, what we have to do is, we have to write add S, again the normal thing, it's addition with the flag should be updated. So there is an S is also there, dot N. So this dot N stands for narrow, in the sense we have to use the 16-bit thumb instruction in that case. That is only the 16-bit will be processed. So that is actually a narrow instruction. On the other hand, I want to particularly use this 32-bit thumb2 instruction, in the sense then you have to put add S dot W. So W stands for wide. So in that case, it will be considered as a thumb2 type of instruction, and 32-bit will be added or subtracted, right? Whatever it is. In this case, actually it is addition, right? So this is actually the general comparison between thumb versus thumb2 type of instructions.